Bismillahirrahmanirrahim. I'm Amal Sohail and my roll number is 21DE04. Today I'll be performing Lab 6 of Digital Signal Processing, which is about discrete Fourier transform properties and fast Fourier transform. The objective of this lab is the representation of discrete time digital signals into frequency domain via fast Fourier transform, resolution of spectrum, computation of magnitude, phase, and power spectrum, and spectrum leaking and avoiding spectrum leaking. Lab 6 is about decimation and frequency method. So the task 1 of this lab is to write a MATLAB program to validate above given decimation. The program first divides the given signal into even and odd samples, calculate DFT for even and odd samples separately, and then merge both of them using this formula, where G of k is the DFT of the even part and H of k is the DFT of the odd part, and WNK represents the Gödel factor. So let us observe the MATLAB code. Here we can see this MATLAB code is designed to process a given signal x by dividing it into even and odd components. It then computes a discrete Fourier transform using the FFT algorithm, fast Fourier transform algorithm. After obtaining the DFTs for the even and odd parts of the signal, the code merges them together using a specific formula, which is here. It represents the odd components and even components along with the Gödel factor, which is represented by the exponential function. So, once the DFT is obtained, the code applies the inverse fast Fourier transform to reconstruct the original signal from the frequency domain back to the time domain. Here it represents the inverse fast Fourier transform function. Let us observe the output. Here we can see the code provides detailed outputs including even parts, odd parts of the signal, the DFTs of the the DFTs of these parts, the merged DFT, and the reconstructed signal. Additionally, it visualizes the original signal and also along with its magnitude spectrum. Task 2 of the lab is check the above program for the signals given below x1, x2, x3, x4, x5, x6, x7, and x8. Observe and find any symmetry in frequency representation. Also match the calculated DFTs with standard MATLAB function FFT of x. Let us observe the code. Here we have created my DFT function that computes a discrete Fourier transform of a given signal x, and then it divides the input signal into even and odd samples, calculates DFT for each sample using FFT function, and merges them using the specified formula of DFT. Now let us observe the code of the task 2. Here we can see this MATLAB code compares the discrete Fourier transform results obtained using a custom function called myDFT with those obtained using the standard MATLAB function FFT. It provides visualizations of the magnitude spectrum for each signal using FFT results. So the given signals are created from x1 to x8. The loop iterates over each signal in the signal cell array, which is created here. Then for each signal, the signal is extracted from signal cell array. The DFT is calculated using the custom function, which is myDFT, and stored in xcustom. Then the DFT is also calculated using the standard MATLAB function FFT and stored in x underscore FFT. The DFT results for both methods are displayed using Dsp function. Then inside a loop, a subplot is created to visualize the magnitude spectrum for each signal using the FFT results. The subplot arrangement is organized to display each signal spectrum in a separate plot. Let us observe the output. Here in the command window, we can see the custom DFT results from the functions we have created and the results from the standard MATLAB function. And we can also observe the magnitude spectrums for each signals provided. Task 3 of the lab is check the program in task 1 for the signals given below and compare it with standard function. Let us observe the code. This MATLAB code compares the discrete Fourier transform results obtained using custom MyDFT function with those obtained using the standard FFT function for the discrete Fourier transform algorithm. It also visualizes the magnitude spectrum for each signal using the FFT results. The signal x1 and x2 are processed in a loop. For each signal, the DFT is calculated using both methods by the method of custom DFT function and built-in DFT function, which is represented by fast Fourier transform algorithm. The results are displayed and the magnitude spectrum is plotted in separate subplots for each signal. Let us observe the code. Here we can see the magnitude spectrum for the signal x1 and also for the signal x2. And in the command window, we can observe the custom DFT results by our own function and FFT result of the built-in MATLAB function. Task 4 is we can further subdivide the above decimation up to 2 samples and calculate the DFT of 2 samples. Then 2 sample DFT added to form 4 sample DFT and 4 sample DFT form 8 sample DFT and so on. This 2-point decimation is called radix 2 fast Fourier transform algorithm. The task is to write a program myFFT that transform a given signal into frequency representation using radix 2 FFT algorithm. Now let us observe the MATLAB code for this task. Here we have created myFFT function which computes a discrete Fourier transform of a given signal x using a custom approach. Because we have created a function by ourselves, it divides the signal into even and odd parts, calculates the DFT for each group separately using the standard FFT function, and merges them using a specified formula provided here. The function then displays the even and odd parts of the signal as well as the DFTs of these parts and the merged DFT for analysis purposes, and then it returns the merged DFT as the output. Now in the calling section, let's call this code. Let us call this function basically. Now in the command window, we can observe that we have gained the even breakdown of the signal, also the odd breakdown of the signal. Then we have observed DFT of the even samples and odd samples, and finally obtained the merged DFT of the provided signal. Task of this lab is to calculate fast Fourier transform using your own function, that is the function we have created in task 4. Compare it with standard function of calculating DFT for the following signals. Let us see the MATLAB code. This MATLAB code compares the results of fast Fourier transform obtained using a custom function myFFT with those obtained using the standard MATLAB function FFT for multiple signals. 4 signals are defined within a cell array signals. Then a loop iterates over each signal in the signal cell array. For each signal, the FFT is calculated using the custom myFFT function and stored in myFFT result. The FFT is also calculated using the standard MATLAB function FFT and stored in FFT result. The results of both methods are displayed and compared. The loop continues until all the signals have been processed. So let us observe the output. Here we can observe the results from standard MATLAB function, which is FFT, and the customized MATLAB function of fast Fourier transform, which is myFFT. Overall, the code evaluates and compares FFT results obtained from both custom function and the standard MATLAB function for the provided signals. Thank you so much for watching. See you in the next video. Allah Hafiz.